We'll get started in just a minute. Pick up where we were left off there in lecture. And again, like normal, this is going to be recorded, so you'll be able to see it when it gets posted if you need to. Again, and again, if you keep the videos off and all that, so I could actually see my screen, that'd be great. And just like in lecture, if you do have a question, feel free to type it in on that box. So again, as I said towards the end of lecture there, my goal here is to try to get through this chapter again to some nomenclature, just to kind of set us up a little bit back on course in terms of lecturing. And that also should allow you to kind of work through those study assignments that technically, where it's on the schedule for today, at least through next week and stuff like that. You could at least get a jump on that or start working on some of those guys as they will be due at some point. And I will post up on Canvas, the due dates for those study assignments as well. So my anticipation, like I said in lecture, is they probably won't be due for a little bit of time. But I just like to get through the material so you can at least kind of work through them at your convenience when you do have time to work on them. Okay, so we've been talking about, and we'll just pick up from where we left off here in lecture. We're going to pick up with talking about empirical formulas and doing a combustion reaction to allow us to basically calculate the empirical formula. So in this example is basically going through what we were talking about at the very end there in lecture, was basically doing a combustion reaction. So we have something like ethanol here, and really ethanol is made up of only really three elements, very much like a lot of organic compounds. They're made up of really three basic elements. Carbon and hydrogen is your basic sort of organic elements in those compounds, and then oftentimes oxygen's involved as well. So when we look at something like ethanol, it's really made up of those three elements, which is why it works really well to do a combustion type reaction and combustion analysis, because we do collect that H2O and that CO2, and that basically just leaves us that oxygen in terms of what we need to basically figure out. So when we do this analysis, like we said before at the end of lecture there, the combustion basically is the carbon, hydrogen, and oxygen here, along with our O2, and we will collect basically water. It'll basically be absorbed here through this little column, and also the CO2, which will be absorbed as well. And as we mentioned at the end there, we're really going to use the CO2 as really to figure out how much carbon was originally there. And the idea there is all the carbon that pretty much would end up here had to come from our original source of carbon, from our ethanol. And the same thing for our water. The water, again, is going to be our source of hydrogen. And with the same idea there, that all the hydrogen that ends up in water had to come from our ethanol to begin with. And as we mentioned before, that's going to allow us to eventually, as we do the calculation, to figure out there. We have to really the oxygen here involves adding oxygen in. So because we're adding oxygen, ends up in this oxygen on the water, and not say nitrogen. So if we were and we were 20 grams of CO2, 13.5 grams of water, we could use that information to figure out how many grams of carbon and how many grams of hydrogen we started with. And we would do a calculation very much like what we did at the beginning of lecture today, where we calculated, for example, how many atoms of hydrogen there were, or how many grams of hydrogen there was instead of in the entire actual compound. So if we start with carbon, for example, to find the mass of the carbon, we would take the 22 grams of CO2, and we are going to want to convert it into moles. And that's because what we're essentially going to do is we're going to use that formula like we talked about earlier today to find a conversion factor. So we can say from this formula that in 1 mole of the entire thing, there would be 1 mole of carbon, again, from the little number on the bottom. We also could, in this case, although we don't need it, 1 mole of CO2 would give us 2 moles of oxygen. But in this case, we're actually interested in carbon. So the first part of the calculation that we want to do, because again, we have grams of CO2, we actually want to use that to figure out just the carbon part. So we're going to use the molar mass of CO2, and that's what the 4401 number is here. That is from the periodic table. And that's the molar mass, right? And now that would leave us with moles of CO2. And that is where we could use the relationship that we have from the actual equation, that 1 mole of the entire thing equals 1 mole of carbon. So that would be the next part of the calculation. And what that's again going to do is cancel out our moles of the entire thing. And now we're left with just carbon, which again is ultimately what we're interested here from the CO2. But we don't want moles of carbon, we want grams of carbon. So then we need to use the molar mass of carbon from the periodic table, and that is 12.01 grams per mole from the periodic table. Again, this being the molar mass from the periodic table. And that's going to cancel out our moles and obviously leave us with grams of carbon. So kind of doing a very similar calculation to what we did at the beginning of lecture, we were able to figure out that from that 22 grams of CO2, 6 grams of it is carbon, and all 6 of those grams of carbon had to come from the ethanol, as that's the only source of carbon in this particular sort of reaction that we did. Any questions on that part of the calculation? And again, if you have questions, feel free to type them in. So again, we would then do the exact same type of calculation for water. The difference is here, when we collect water, we're really interested in basically the H part of water. And we can see from the formula, H2O, that for every 1 mole of H2O, we get 2 moles of just the hydrogen part. And that again is going to be a conversion factor that's going to allow us to go from the entire thing, the H2O, to just the hydrogen part. Because remember, the goal, what we're really trying to do here in the first part of the calculation, is to figure out the mass of carbon, hydrogen, and oxygen in this compound. So we need to do this calculation based on the amount of water that was collected to allow us to basically figure out how many grams of hydrogen that would be. So we would start the calculation the same way, except that we would start with the mass of the water that was collected. Again, we're going to have to convert the water into moles. So we would go to the periodic table, use the molar mass of water, which is, again, what this number is here. That's the molar mass of water from the periodic table. That's going to convert our grams of water into moles of water. And then we could use the relationship that we have up on top, that for every, again, 1 mole of water, we get 2 moles of hydrogen. So that's going to allow us to go from the whole thing of H2O to just the hydrogen part, because that's what we're interested in. And again, same thing as above, we're not interested in moles of hydrogen, We're actually interested in how many grams of hydrogen that was. So the last thing that we need to do is use the molar mass of hydrogen. Again, as we talked about in class lecture earlier, whenever you do molar mass, even though there's like a 2 or whatever it may be, it is just based on the formula. So it's 1.008 grams per mole. And that will cancel out our moles of H, our water of H is canceled, and our grams of H is canceled. And that will tell us that from this reaction, we basically collected 1.51 grams of hydrogen. The same idea here is all of that 1.51 grams of hydrogen all had to come from the ethanol that was in this reaction. Any questions on that part of the calculation? And again, here in the middle part of it here, we're using the actual chemical formula as a conversion factor. So that's where we get those guys from there. And then also, that's where we get that from, is the actual chemical formula as a conversion factor. Any questions on that part of the calculation? So as we were talking about towards the end there, lecture, once we do a calculation like what we have on the board here, that will give us the grams of carbon. That will also give us the grams of hydrogen in this case. So once we get those, that's going to allow us to get the mass of the oxygen by subtracting those two. So we would subtract the mass of the carbon from the mass of the hydrogen, and we would take the mass of the compound minus those two guys. And that's what we're going to do on the next page, and it'll be much neater than what I just tried to write there. So let's take a look at that. So if we take those numbers, we take the mass of the compound that we started with, and if you remember in this problem, we started with 11.5 grams of ethanol that we basically did this combustion reaction with. So again, this number was given to us in the problem. And we're going to subtract the mass of the carbon here that we calculated on the previous page, and the mass of the hydrogen that we also calculated on the previous page. And that's going to tell us that, if I didn't scribble in front of it, that we had 4 grams, right over here, 4 grams of oxygen, basically. And now at this point, we have the grams of carbon, we have the grams of oxygen, and the grams of hydrogen. After doing all that calculation, you can now actually do the empirical formula calculation. So we want to take the grams of each of those elements, and we want to convert them to moles. And if we do that, that's what we'll see next here. So we're going to take the grams of carbon that we calculated, again using the molar mass from the periodic table. We're going to convert that into moles of carbon, which gives us 0.5. We then are going to take the grams of the hydrogen that we calculated on the previous page, and we're going to use the molar mass of hydrogen from the periodic table, and that will give us the moles of hydrogen. And now that we have the we have the grams of oxygen, we can take the grams of oxygen and divide it by the molar mass of oxygen from the periodic table, which is 16 grams per mole. And at this point, we then want to divide by the smallest number of moles, which in this case, it looks like the smallest number of moles there is our oxygen. So we're going to divide everybody by that 0.25 moles. And if we do that, we're going to divide the 0.5 by the 0.25, the 1.5 by the 0.25, which is the smallest number of moles. And we end up with 2 for carbon, 6 for hydrogen, and 1 for oxygen. And again, since those are all pretty much whole numbers, that would give us our empirical formula for ethanol of C2H6O. So once we got to sort of this page, this is just like what we did previously. These are all the same basic empirical formula steps. The only sort of additional calculation you have to do in a combustion problem is what we did on the last page. And again, what we did on the last page, the goal of that was to get the grams of carbon, oxygen, hydrogen, so that we can then proceed through our empirical formula steps. So a combustion problem is just a little bit longer in terms of the calculation part. And that's again because you have to do that calculation to figure out the grams of the carbon, oxygen, hydrogen. And once you have those, you then can just go through your normal empirical formula steps. Any questions on any of those steps there? Where any numbers came from or anything like that? Okay. So these are two common ways that you can sort of calculate the empirical formula. Again, the basic steps for in both of them are essentially take the grams of each element, convert them to moles, divide by the smallest number of moles. And again, if you get all whole numbers, that would be your empirical formula. And again, in the combustion analysis, the only additional steps that you have to do is you have to do a little bit more calculation to figure out how many grams of carbon and hydrogen there are coming from both the CO2 that was collected, that will tell you the carbon, and the H2O that was collected, that will tell you the hydrogen. And once you get the carbon and hydrogen grams, you could use that to figure out how many grams of oxygen. Any questions on empirical formulas or how to calculate them? Okay, so the next thing we're going to talk about then is the molecular formula. So as I mentioned earlier, the molecular formula is the actual formula that tells you exactly in that particular compound how many of each elements you have. And to calculate the molecular formula, you really need three basic things, which is essentially what's on the screen. Really, the three things you need is you need the empirical formula. So either you need to calculate the empirical formula like we just did in the previous examples, or they may just straight out give you the empirical formula and you can obviously have it. But one way or the other, you need to get to that empirical formula. Then, like it says up here, what you basically need is the molar mass of that empirical formula. And a lot of times that is not given to you. So once you figure out the empirical formula, you need to go to the periodic table and figure out the molar mass of the empirical formula. And then the third thing that you need, which is usually given to you in these type of problems, is the molar mass, like it says up here, of the compound. And in a textbook problem and in most problems that you come across, this is usually given to you. Yeah. So this is usually given in the actual problem itself. It will say something in the problem like the apparent molar mass of the compound is 186 grams per mole. It may actually even give you a range, like the molar mass is somewhere between 90 and 200 grams or something like that. But somewhere in the problem, they will give you the molar mass of the compound. And so that is usually something that you don't have to worry about sort of calculating or anything like that. You usually could just find it. And once you have all three of those things, you basically are going to take the molar mass of the compound, which is given to you in the problem. And you're going to take the empirical formula, which usually you got to calculate. And you're going to divide it, and it's going to give you a number. And in most cases, this number will be a whole number. I would say in terms of the only point where it's usually pretty okay to round, even if you're not exactly super close to the whole number, is when you're doing this part. Yeah. I would say in most cases, it will give you a pretty close to whole number when you divide it. But in some cases, you may not get exactly a whole number, but it's okay to round when you're doing the molecular formula part. And that's because the relationship, as we talked about earlier today, is between the molecular formula and the empirical formula. It is basically a whole number ratio, the difference. So this was a 2-to-2 ratio. This is a 1-to-1 ratio. and it basically is a whole number ratio between these two. Um, so, something like the other one that we saw was this. They are related to each other really by a whole number factor between, say, the empirical formula and the molecular formula. So that's why in all these places, really this one here, when you divide these two numbers, it's really okay to round if it's just off of that whole number. But in most cases, especially in textbook problems and so forth, you typically will get a pretty clean whole number when you divide it, or something very close to a whole number like 1.999 or something like that. So it'd be very, very close. Any questions on that? All right, so let's take a look here. So why don't you give this a go? A sample of a compound that contains boron and hydrogen contains 6.44 grams of boron and 1.803 grams of hydrogen. What is the molecular formula of this compound? Boron is 1081 in terms of its molar mass from the periodic table, 1081. And hydrogen is 1.008 grams per mole. All right, so why don't you give it a try and see what you come up with, and then we'll talk about it in just a second. Okay, so let's take a look and see how we're doing here. So in this case, we're looking for the molecular formula. And in order to calculate the molecular formula, again, there's three things that you need, which is the empirical formula. You also will then need the molar mass of the empirical formula, and then obviously the apparent molar mass of the compound, which is right here. So again, that approximate molar mass of the compound is essentially given to you. And in this particular example, we are not given the actual empirical formula, which means we do need to calculate it. So the first thing that we would want to do is, just like what we did in the previous examples, we want to take the grams of boron and the grams of hydrogen, and we want to convert them into moles using the molar mass from the periodic table. So that's the 10.81 grams of boron per mole and the 1.008 grams of hydrogen per mole, grams per mole. So the first thing we would do is take those grams that were given to us and calculate the moles of each of them, again by using the molar mass that we find on the periodic table. And it looks like if we do that, we end up with 0.5961 moles of boron and 1.789 moles of hydrogen. Any questions on that so far? So again, here we're trying to calculate the empirical formula. So the first step is converting those grams into moles. Again, we always want to divide when we're doing empirical formula by the smallest number of moles. So in this case, it is going to be our boron, which is the smallest number of moles. So we want to divide each of those numbers by 0.5961. And if we do that for the hydrogen, we end up with 3. And obviously, if we divide boron's moles by itself, we end up with 1. And in this particular case, because we did hit whole numbers here, that means that that will give us our empirical formula of BH3. Any questions on how to get to that empirical formula? Again, it's the same basic 3 steps. We're converting our grams to moles. We're dividing by the smallest number of moles. And again, since we did get all whole numbers, that would be our empirical formula. Any questions on this problem up until this point? Okay, so now we have pretty much 2 of the 3 things that we need. We have the empirical formula that we had to calculate, and that's very common that you do have to calculate these things. And we do have the molar mass of the compound that was given to us in the problem. So the third thing that we need to actually calculate the molecular formula is we need to calculate the molar mass of this empirical formula that we just did. And since we have 1 boron and 3 hydrogens, using the molar mass from the periodic table, we will see that the molar mass of our empirical formula is 13.834. And that is essentially the third thing that is needed to calculate the molecular formula. So now we essentially have everything that we need to calculate the molecular formula. We want to take the molar mass that was given to us, which in this case is 30, and we want to divide it by the molar mass of the empirical formula, which is 13.834. So again, this is the molar mass of the compound, which was given. And this is the molar mass of our empirical formula. So when we do divide those 2 numbers, we actually get a number that is 2. If you actually do it on your calculator, you're going to get something like 2.16. We're technically at 2.16, like 9-ish. And this is what I was saying before. When you do the molecular formula part, where you're doing this division part, it's okay to round to the nearest whole number in most cases, and that would be a 2 in this case. And that means that what we want to do is multiply our empirical formula by 2. So you could do it one of two ways. You could distribute the 2 to each of them. So that would give us B2H6. Or sometimes people will write the empirical formula in parentheses and put the 2 on the bottom. Most people will probably distribute it to each of them, and you'll get your B2H6. Any questions on those steps? So again, in some cases, a problem may actually just give you the empirical formula, which means you pretty much could just skip to the step where you get the molar mass of it and do the division part. But a lot of problems, you have to usually first calculate the empirical formula. And then once you calculate the empirical formula, you could calculate the molecular formula. Any questions on any of those there? Okay, let's take a look at another example, I think. So why don't you give this one a go here and see what you come up with. And phosphorus from the periodic table is 3097. So phosphorus, 3097 grams per mole. And then oxygen is 16 grams per mole. So again, here we're looking for the empirical formula and the molecular formula of this particular compound. So why don't you take a couple of minutes or so and see what you come up with. Again, if you have any questions, feel free to type them into the box. Okay, so let's take a look and see how we're doing. It's looking like we're doing pretty good here. Yeah. All right. So again, when we look at it, we're given the percent composition by mass of each of those elements, the phosphorus and the oxygen. And remember that when you are given like those percent compositions by mass, you want to just quickly kind of just add it up, make sure it's about 100%, which in this case we got like 56 and 43-ish or 4. So we're about at 100%, which means we're not missing any elements. Again, here we're looking to calculate the molecular formula and the empirical formula. And that's good because we do need the empirical formula. We also need the molar mass of the empirical formula and the molar mass of the compound, which again in this case was given to us, which is 283.89 grams. So to convert our percentages into grams, we're just going to assume 100 grams, and the reason again why we assume 100 grams, you could technically assume any number you like, but when you assume 100 grams, the numbers remain the same, so you don't have to change any numbers. So if we assume 100 grams, we're going to take our molar mass from the periodic table and convert both of those guys into moles. So again, this comes from our periodic table, the molar mass. We're going to convert each of these into moles. And just like normal, when we do our empirical formula, we want to divide always by the smallest, which in this case is our phosphorus at 1.4. So we're going to divide both the phosphorus and the oxygen by that 1.4. And that's going to give us a nice number there for our phosphorus of 1. It will give us a 2.5 in terms of our number there for our oxygen, which means if we were to sort of write the empirical formula at this point, it would be P1O2.5. And as we talked about, this part right here is not good. So when you do the empirical formula, you do need a whole number. And this 0.5 is too far to round. So in this case, we need to find a number where we can multiply this empirical formula by over here to get everybody to a whole number. So if we just kind of do quickly, if we take 2.5 times 1 is 2.5. We take 2.5 times 2, it is 5, which is a whole number. So the key here is sometimes people mess up. You actually want to multiply by the factor, not the number. And the other thing that people mess up is, again, you need to multiply both of these guys by the 2. So if we distribute that 2 across that empirical formula, we will end up with an empirical formula of P2O5, which looks like what some people got up there in the chat. So that's good. Any questions up through the empirical formula here? Now, to get the empirical formula, because it was asked for in this question, it's important, but it's also just as important here if we were to calculate the molecular formula, which is what we need to calculate as well. So now that we have the empirical formula, we want to use it and get the molar mass of it. So we would go to the periodic table and take 2 times the mass of phosphorus, which is the 3097, plus 5 times the mass of the oxygen, which is the 16. And that gives us the molar mass of our empirical formula of 141.9. So the last thing we need to do to get to our molecular formula is to take the molecular formula that's been sitting here in our problem up here, the 283.89, and we're going to divide it by the empirical formula's molar mass, and that gives us a number around 2. So again, when you put that into your calculator at 283.89 divided by 141.9, you end up with 2.0000, which again is obviously a 2. And again, the answer for the molecular formula is not 2. It is actually what you do with that 2, which is you then need to multiply your empirical formula by it. So the molecular formula would be P4O10. So P4O10 would be our molecular formula. Or again, sometimes people will write it like this, but most of the time people will distribute that to, for example, across. So just so everybody's clear, this number here is not the answer for the molecular formula. It is just the factor by which you need to multiply the empirical formula by so that you can get the molecular formula. And the correct answer again for the molecular formula, P4O10. Any questions on any of those steps there? Any questions on how to calculate empirical formula, molecular formula, combustion analysis, any of those things from this chapter? This also should help you with experiment 7, which I believe is empirical formulas and molecular formulas. So pre-lab, post-lab questions should, if I remember correctly, be similar to these type of questions. Any questions on the lecture here or how to calculate those things? Now, if I'm not mistaken, I think we got one more example. So I'll tell you what you do for this example. Yeah, why not? Extra credit, yes? All right. So you could do this one for extra credit, and I'll put up on Canvas an assignment for it, and you could submit it to me over the next week. I'll put it up there. Next couple of days, I'll put it up there, but you could turn it in sometime before the end of next week, and I'll give you some extra credit for doing this example. So with that, we're going to finish this chapter in terms of molecular and empirical formulas, grams, moles. Is there any questions on this chapter before we go into the next one, which is about nomenclature? Okay. Any questions on it? And like I said, this now should allow you to complete, after this chapter here, that the study assignment, which I think is labeled units, and I think it's study assignment D. And you should be able to complete the calculations for experiment 7, which is empirical formulas, molecular formulas, I believe, as well. Any questions on any of that? Okay, so we're going to then continue lecturing for just a little bit into some nomenclature. But what I'm going to do is stop sharing so I don't accidentally show you the answer to the extra credit. So let me hit that first, I think. And just give me a second. I'll put it back, something back up in just a second. Okay. Now, I think I want to hit that. And I want to hit that, I think. There we go. And oops. Give me 1 second here. Let's do it that way. I think that might work better. Okay, let's try this again. Let's see here. Okay. Get you in there. Technology, make things easier. Let's try this again here. Let's see here. Close down some of these things. All right. Third time's a charm, maybe. Let's see. Let's go here, maybe. All right. I think you see it now. Sorry about that. Okay, so we're actually going to continue on to nomenclature, which is the next topic there. And so this is actually back to chapter 3, and it's the very last part of chapter 3 that we see here, which I think is 3.12. There we go. Okay. Back. Stay, maybe. There we go. All right, so nomenclature, which is about naming, is from chapter 3, and it's the very last section, I think, of chapter 3. And we're pretty much going to talk about how to name everything you ever wanted to name, or maybe didn't want to name, and stuff like that. So let us start. That's a periodic table, in case you forgot. Hopefully not. Still a periodic table. Still hasn't changed. Looks great. All right. So when we talk about nomenclature, we're going to really talk about how to name 2 types of compounds, and a couple of reminders just in case. One type of compound is an ionic compound. And like we talked about with Lewis structures and all that, I think we did. An ionic compound is between a metal and a non-metal. And in a metal-non-metal combination, what happens is we get an electron transfer. And the result of that is the metal loses an electron and it becomes positively charged, which is known as a cation. And that is a positive charge. Well, the non-metal basically picks up an electron, 2 electrons, however many electrons they decide to get rid of that day, and becomes negatively charged. And the important thing is, like we talked about with bonding, is when we have a cation and an anion, something that is positively and negatively attracted to each other, what holds that together is that electrostatic attraction. And the key here is, as we talked about, there is no sharing of electrons. So we have no sharing of electrons here. And that is different than, say, a molecular compound, which is kind of our covalent bonding that we talked about. And with our covalent bonding, we have basically 2 nonmetals. And when we have 2 nonmetals, basically we do have sharing of electrons. And as we talked about with bonding, that may be shared equally, right? And that's how we get our nonpolar bond. Or it may be shared unequally. And that's how we get our polar covalent bond, right? But there's some aspect of sharing of those electrons that are happening. So when we talk about nomenclature and how we name these guys, they're actually named differently depending on the type of compound that we're talking about. So we will start probably focusing first on ionic compounds, and then we'll get to molecular compounds after that. Any questions on sort of that? That also brings us back to our periodic table that we kind of jammed through. The important part here, when we talk about nomenclature and we talk about naming and writing chemical formulas, is basically charges on the periodic table. So a reminder that things in group 1 will make a +1 charge. Things in group 2, which are metals, will make a +2 charge. Over here, really, it's aluminum. When group 3 will make a +3 charge. We don't really have a good pattern here for group 4. But starting at group 5, and we're talking really about our nonmetals, so our guys above the staircase here. In group 5, they become negatively charged because they gain electrons, so -3, -2, and -1. So these are things that have basically fixed charges. So again, if you have something like lithium, when it does make a charge, it's always going to be +1. You'll never find a lithium with like a +3 charge because it just doesn't happen with lithium or anything like that. It's always going to be +1 no matter what the situation is. So these are really kind of things with sort of fixed charges. Now, transition metals, which are right there in the middle, transition metals. Transition metals, they can have a variety of charges or variable charge. So, for example, that's a very badly spelled variable charge, but they can have variable charges like copper in certain cases can be copper 1, in other cases it may be copper 2. Iron, for example, can be +2 in certain cases and maybe +3 depending on who it's sort of bound to. And in addition to the transition metals, although they're technically not transition metals, everybody in this range as well, usually over here, these guys included, things like tin, lead, antimony, bismuth, these guys also can have a variable charge. So, for example, lead in certain cases could be +2, lead could be +4 in other cases. So it depends. So, although they're not technically transition metals in terms of naming and sort of how we think about them, we do sort of think about them as sort of transition metals as well. Now, most transition metals do have that ability to make sort of a variety of charges. There are sort of 3 exceptions in the transition metal region that basically have a fixed charge, and that is zinc, which has a +2 charge no matter what the situation is. That is also cadmium that has a +2 charge no matter what the situation is. And then if you kind of hang a leftover to silver, silver will have a fixed charge of +1. So zinc and cadmium, no matter what the situation is, will have a fixed charge. Silver will also have a fixed charge of +1. But everybody else in the transition metal region, again, will basically have a variable type charge. And again, guys in group 1, 2, and 3 will be +1, +2, and +3, while 5, 6, and 7, the non-metals will be -3, -2, and -1. Any questions on sort of charges on the periodic table? Also, a reminder while we're talking about charges on the periodic table, things only get charges when they pretty much start to combine. So if you had sodium metal by itself in the solid form, no charge. Yeah. If sodium hooks up with chlorine, that is when the sodium actually gets the +1 charge. So if you just take the element off the periodic table and it's not combined with anything else, it won't have a charge. Again, really things as we'll talk about get charges when metals and non-metals pretty much come together and bond. Any questions on sort of that there? Okay. And yeah, put a periodic table up here for some reason, right? That's good. So when we talk about just ions by itself, either a cation or an anion, and this table is not from your book, but you probably have a similar table. In terms of our cations, in terms of how we name just the cation by itself. So if you were asked to write the formula for a cation for any of these, they would look like this. And because it is an ion, they would have their appropriate charges. And how we name pretty much cations is we pretty much just use the entire name of the element. So come back here. We use the whole name of the element. So much like it says up here, if you have Na+, that is your sodium ion, the whole name. If you had Ca2+, that would be your calcium ion. Again, we just use the whole name. And if it's just that ion by itself, a lot of times we will include ion at the back end of it. Now, when we talk about anions, which are typically our nonmetals, we basically will use the root of the name and end it with IDE. So as you can see here, nonmetals, pretty much you use the front part of the name, you drop the last part, and you insert IDE in here. So again here, O, which is oxygen, we drop the last part of the name there, put the IDE, becomes oxide. This is bromine. Again, we drop the last part of the name there and put the IDE on it. So this is very typical in nomenclature. The negative guy or the anion will end in IDE. And same thing, much like we see up here, if we have Cl minus, that is the chloride, IDE, ion. If you had, again, the O2 minus, that would be your oxide ion, as you can see up there. You will also see up here as well, hydrogen is one of the only ones that pretty much can do both things. It can become a cation in certain cases, as it is over here, or it can become an anion, as it is over here. So again, if you have the H+, that is your hydrogen ion. And when hydrogen actually comes second in the formula behind a metal, like something like LiH, that is what is known as lithium, and this H here is H minus, and that would be lithium hydride, IDE. So hydrogen has the ability basically to become positively charged. It also has the ability to become negatively charged. And usually hydrogen will only become negatively charged when it follows a metal. So when it follows a metal, like lithium is a metal, that's typically when you'll see the hydrogen become negatively charged. So if you were asked to write the formula for the anion, this would be the formula for the anion. Just like these guys over here, again, would be the formulas for the cations. And if you have just the ions by itself, just like the positive guy, if you have the anion by itself, it also should have the charge included with it. Any questions on that there? So let's start with talking about how to name ionic compounds. They're sometimes called type 1, type 2, and type 3 when we talk about naming compounds. And when we talk about naming type 1 and type 2 compounds, those are ionic compounds. So here a type 1 is an ionic compound. And again, it's that combination of metal and non-metal that comes together. And always when you have a metal and a non-metal that comes together, the metal is always the important one. Yeah. So the metal is always the one that you want to look at. It's always really going to tell you how to name a particular compound. And when we have a type 1 compound, the metal here comes from group 1, 2, 3 from the periodic table. R is zinc, cadmium, or silver. And if you remember, what all of those basically have in common is they have fixed charges. Which means, as we talked about, if you have sodium ion, no matter what the situation is, sodium will always be +1. It will never be anything other than +1. And because they have a fixed charge, the nice thing about it is when we go to name it, we essentially will use the whole name of the metal and our nonmetal will get the last part of the name dropped and replaced with IDE. So that's really sort of the nice thing about these guys, just the whole name and then the nonmetal IDE at the end of it. So that's why when we look at something like sodium chloride here, or NaCl, we look at it, sodium is a metal, Cl, which is chlorine, which is a nonmetal. So our sodium is group 1 on the periodic table, which means it has a fixed charge. So you could just proceed directly to the name, whole name of the metal, which is sodium. The chlorine becomes chloride at the end of it, and we get sodium chloride. Although when we see the formula for an ionic compound, it should never have a charge. And what I mean by that is when we look at the formula here of NaCl, there should be no charges ever written in a formula when you put a metal and a nonmetal together. And what we want to do is really balance out the positive with the negative charge. We want to make sure it equals 0 when we put it together. So although sodium chloride written like this has no charge, it is actually made up of two things that do have charges. It is made up of a sodium ion, which is group 1, which has a +1 charge. It is also made up of a chloride ion, which is group number 7, that has a -1 charge. This would be our cation formula. This would be our anion formula. And when we put that together, we have +1 and -1. So that gives us 0, and that is why we need just one of each of those to get the correct formula. Any questions on that? Now, if we have something, say, like CaBr2, for example, when we look at this, Ca is calcium, which is a metal. That's our metal. Br, which is bromine, which is a nonmetal. This is group 2 on the periodic table, which means calcium has a fixed charge of +2, no matter what the situation is, which means to name this, we would go calcium, whole name of the metal. And now our nonmetal becomes bromide, yeah, IDE. We drop the last part of the name. Now, a couple important things about this name and what people for some reason always want to do is what we see here is we have a 2. And what you could hopefully see here is it has no effect on the name. People for some reason always want to put dibromide or something like that and use a prefix. For type 1 compounds, you should never use a prefix. It has no effect. If that 2 there was like 40, it still wouldn't matter. It would still just be called bromide. So this is calcium bromide, which would be the correct name of it. Let's talk about why the 2 is actually there. The 2 is actually there because when we talk about calcium, which is group number 2, it has a +2 charge, which is our cation. And when we talk about Br, that is group 7, which has a -1 charge, and that would be our anion. The problem, though, if we just slap those two guys together just the way they are, the +2 and the -2 would equal +1 that's left over. And again, when you put something that is positive together with something that is negative, it needs to equal 0, which means in this particular case, we need actually 2 of the Br minuses to balance out the charge. -1 and -1 gives us a -2 that balances out nicely the +2 that we have here. And that is why the correct formula here is CaBr2. But even though there are 2 bromides here, it has absolutely no effect on the name, and you shouldn't do anything like di or anything like that. Question on that? And if you remember, the real reason, for example, why we need those 2 it actually goes back to our bonding that we talked about in those chapters. Calcium, which is group 2, has 2 valence electrons, right? And bromine, which is group 7, has 7 valence electrons. And if you remember, the whole point of ionic bonding and all bonding, right, is for everybody to achieve basically that noble gas configuration. So if you remember, as we talked about, when calcium loses an electron over to the Br, that is when it would gain a charge. But once it accepts that 1 electron, bromine here is full, which means calcium is not happy because it still has 1 more electron to give. And if you remember, if you look at the periodic table, a really bad drawing of the periodic table, right? There's calcium. And remember, his goal is to get back to the noble gases. So if he loses just 1 electron, it only moves him back 1 spot to basically potassium's location. But he doesn't want to get to potassium. He basically wants to get back to argon's location. So he wants to lose that 2nd electron, and the only way he could do it is he needs that 2nd Br there basically to take that 2nd electron from them and become minus charge. So really the basis why when we take a positive and negative guy and put them together in terms of equaling 0 in terms of the charge, and sort of the simplest way for them to equal 0 is because really that allows everybody to reach that noble gas configuration and be really sort of stable. Any questions on that there? So here's a prettier picture, I guess, than what I scribbled on. But again, this just shows you the charges. Everybody in group 1 is +1. Everybody in group 2 is +2. Everybody there in group 3, which again is typically your aluminum, will be +3. And again, our transition metals here are our zinc will be +2. Our cadmium will be +2. And again, our silver here will be +1. These 3 transition metals being exceptions. And again, going backwards here, -3, -2, and -1 are typical charges. So let's take a look at these guys here, and why don't you guys take a second here and name each of these, and then we'll talk about it. Just take a minute or two, see what you come up with in terms of the name. All right, so let's take a look. So again, we have K, which is potassium. Very good, looking good, I think, on the chat there. And Cl is chlorine. So K, which is group 1, tells us it's a type 1 compound because it has a fixed charge. So again, we would just use the entire name of our metal, and then our chlorine becomes chloride at the end. Very good. And our zinc, which is not group 1, 2, or 3, but it is one of those transition metals that has a fixed charge. Again, along with cadmium and silver. And zinc will always become a +2 charge. And because it has a fixed charge, you do not need a Roman numeral for that one as well. So that would be zinc. S, which is sulfur, becomes sulfide, IDE. Again, our cation here would be zinc with a +2 charge. Our anion would be sulfur, which is group 6 with a -2 charge. So +2 and -2 again is why we only need one of each of them in our formula. And here our cation would be K plus, and our anion up here would be Cl minus, same deal, +1 and -1 gives us 0 when we put it together. Last one here, we have calcium, which is group number 2 on the periodic table. So also has a fixed charge. So we're going to just use the whole name there, calcium. And then our bromine becomes bromide, IDE. Again, as we see here, as we talked about, the 2 has no effect on the naming, and it should just be calcium bromide. And the reason, again, why the 2 is there is our calcium is group 2, which is +2. And our anion is bromine, which is group 7, which is -1. And again, to balance it out, since this is +2, we need actually 2 of these guys, but again, has no effect on the actual name. Any questions on any of those examples there for type 1? Okay. Oh, there's one more I left off, huh? So we do have the guy on the bottom there that I now just scribbled on. We'll go that way. So Ba is barium, which is group number 2, has a fixed charge. In this case, hydrogen comes second after a metal. So that is going to be when hydrogen becomes negatively charged. And that is why there's 2 of them there to balance out the charge. -1 and -1 gives you -2, balances out the +2. And we again would use the whole name of the metal, which is barium. And our hydrogen here would get the negative version, which would be barium hydride in this case. Any questions on that particular one there? Okay, so that is type 1. Let's talk about type 2. Now, type 2, pretty much the same deal as type 1. It's still an ionic compound, which means we have no sharing of electrons here. And just like type 1, type 2, the metal's important. The metal's going to be a transition metal. Are just to the right on the periodic table, below the staircase where our semi-metals are. So those are things like your tin, your lead, etc. So what these guys have in common, as we talked about, is they can have a variable charge. And because they have a variable charge, you do need to usually figure out what the charge is. But the good news is whatever it's bound to, you typically can figure out the charge of. So the way we name this is the exact same way. We use the whole name of the metal. We still, for our non-metal, drop the last part of the name and add IDE to it. The additional thing that we have to do is we have to use a Roman numeral. And what the Roman numeral does is it indicates the charge, which is the positive charge on a metal. So very common people screw up by thinking that the Roman numeral is how many of the metals that you have. It is actually what you would get if you took one of those metals and what the positive charge would be on just one individual metal. So for example, if we look at FeCl2, Fe, which is iron, is a transition metal. So that automatically should tell you that this is a type 2 compound, which means you may not know what the charge is, but the good news is you will always know what the charge is or what it's bound to. And Cl is group 7, which means it has a -1 charge. And again, there's not one of them there, but there's actually two of them. If we just draw it all out, that overall gives us a -2 charge for our negative side. So because there's only one iron, the iron would have to have a +2 charge, which means that the name of this guy would be the whole name of the metal, which is iron. Here we use Roman numeral 2, which again is not how many metals we have, but the actual charge that we see on the metal. And same deal, even though there's two of these guys here, it has no effect on the name. We just simply would call it chloride, IDE. Any questions on that name? And the reason we need to do that is, for example, if we took FeCl3, we would have sort of the same situation. We would have iron, which is a transition metal. I'm not sure what the charge is. But in this case, we have 1, 2, and 3 chlorides, which gives us a -3 charge. So in this case, the iron is not +2 like it was previously. It's now +3, which means the name of this guy would be iron, Roman numeral 1, 2, and 3. Again, for the charge that we have on it. And then same deal, even though there's three of them, and you might want to say trichloride, don't do it because it's just going to get you one of those, yeah? So you want to just call it chloride, yeah? So this would be iron, Roman numeral 3 chloride. Really naming is just all about telling people really what you're using in that particular case. So in the first case, we're saying, hey, we're talking about the iron that has a +2 charge. In the second case, we're talking about the iron that has a +3 charge. Any questions on that there? So for example, if I had PbO2, why don't you take a second and tell me what you think that might be in terms of the name. If you like, you could type it into the chat and see how you did. All right, so let's take a look and see. So again, lead is not necessarily a transition metal. So let's take a look and see where maybe the difference in your name and this name will be. So lead, which is not a transition metal, but it is one of those ones just to the right of it that's below the staircase that has the ability to make multiple types of charges. But we do know oxygen, which is group 6 on the periodic table, has a -2 charge. And again, here, there's not one of them, but there's actually two of them, which if we add that together gives us a -4 charge overall. And because there's only one lead, in order to balance it out, it would actually have to be, in this case, lead 4. Yeah, so it would actually have to be lead 4 and not lead 2 because of the 2 oxygens that are there. And that means that the name here would be lead, Roman numeral 4. And same thing here, even though there's more than one, we would just call it oxide. Now, you will sometimes see people maybe make this mistake, and it has a lot to do with sometimes how people are taught. So, for example, sometimes people are taught that if you have a formula, say like the FeCl2 that we saw previously, what you could do is like the crossover move, like move the charges or the numbers that way. And in this case, you will get Fe2 plus and Cl minus, which is correct in terms of the charge. And you could also do that, you know, if you have, excuse me, the ions by themselves, you could go down. And if you just had the ions by, you know, if you had, say, calcium and fluoride, you know, you could go this way as well. And I'll tell you, oh, I just need one of those and two of those. And that method works really well for like, you know, 90-ish% of the time. Yeah. So if you do that method, and you will oftentimes sometimes get into some trouble, especially with something like this. So I always find it's best to sort of think about it kind of like this, you know, just to balance it out to 0. But again, if you just kind of blindly do the crossover move, which is very commonly taught a lot of times, you know, you'll probably be right most of the time, but there's a lot of places where you will get the wrong formulas or the wrong names. So, you know, if you can think about it, just the basic idea of I need to get those guys to 0 when we balance it out. Questions on that type 2 or how to name it? Now, when we talk about sort of type 2 guys on the periodic table, here are some type 2 guys. And these guys, come back. These are some type 2. Nickel could have multiple types of charges. These guys really shouldn't be part of type 2 on here. I'll just cross it out there. These guys have variable charges. These guys have fixed charges. Nickel can be something like nickel 4 as well. So nickel does have a multiple charge. So I'll just kind of cross this out. It happens when I borrow that with air quotes from a book. But again, everybody in this region pretty much can have multiple types charges. And again, as I mentioned, in this area as well, they could have the variety of charges. So these are all the guys that will need those Roman numerals. Again, kind of a weird one is Mercury here. So when you look at Mercury like that, or Mercury like this. These are the 2 ions for Mercury. And oddly, the one that has all the 2s in it, like up on top here, is actually Mercury 1. And the one that has like just like 1, 2 is Mercury 2. Yeah. And that's because Mercury 1 comes as what's known as a dimer. So basically, you know, 2 Mercuries kind of hooked together, not correctly like that, but and they both have a +1 charge, but together they kind of move around as like a polyatomic ion, kind of like as one unit basically. So all these guys here will need Roman numerals when you go to name them. So let's take a look at this little chart again, just some examples. We won't use sort of this older way of naming, and this older way of naming, which is over here, uses either IC or OUS, and we won't really use it, but occasionally you may see it. And you can also see that they use more of the historical type name for the elements. So instead of iron, they use ferrous or ferric. And really the one with the ic is the one that has the higher positive charge. And the one with the OUS has the smaller positive charge. So when you look at something like the ferric versus the ferrous is +3, the ferrous is the lower charge at +2. So for our class, and probably most classes you come across, you probably don't have to worry too much about that. column. Most people nowadays use the Roman numerals, but if you see something that's a little bit older or something like that, and some people still kind of use these occasionally, but most chemistry classes you take, they'll probably stick with this type of naming with the Roman numerals. So, so we have a few here. So why don't you take an opportunity here and give those a go and see what you come up with. Whoops, there you go. I'll make sure I didn't miss one. So take a couple of minutes there and come up with the names on those. Okay, so let's take a look and see how you did up there. Looks like got some answers coming through. So when we look at over here, we have our CO, which is cobalt, which is a transition metal. So as soon as you know cobalt's a transition metal, you should know that it could have a variety of charges. So we do want to figure it out. So the Cl, which is group 7, has a -1 charge. And again, there are 3 of them. If you draw them all out, you don't have to. Gives you an overall charge of -3, which means our cobalt in this case does need to be +3 to balance it out to 0. And again, we're going to use the whole name of our metal. Our Roman numeral will be 3 here for the charge that we have on it. And again, just like type 1, this 3 here has no effect on the name. It is just going to be copper 3 chloride. Any questions on that one? So coming here to Cu, which is copper, also a transition metal. So also going to tell us is type 2, has multiple types of charges. We're going to look at what is bound to, which is I, which is group 7, has a -1 charge. That means in this case, to balance it out, it does has to be +1. And that means that this would be copper Roman numeral 1 iodide. Any questions on that one? And lastly here, in terms of our example, we have SN, which is tin. Again, tin is not technically a transition metal, but it is named just like a transition metal. And that means that we do want to look at the Br, which is Br minus from group 7. And we got 4 of them. And again, you don't have to draw them out, but it might just help visualize that overall we have a -4. And that means that this actually has to be +4 in this case. And this would be 10 Roman numeral 4. And again, even though there's 4 of these bromides, it is just bromide in this case. Any questions on any of those 3 there? Don't forget as well that you are responsible to be able to go from the name to the formula. So if you had something like nickel to nitride and you wanted to write the formula for it, the name itself actually here gives us some information. So that is nickel, and we know it has a +2 charge because of the Roman numeral. And nitride is nitrogen from the periodic table, and that's group number 5. And that means it has a -3 charge. So if we put these together, +2 and -3, the common number there is 6. So to get our nickel to 6, we need 3 of them. And to get our nitrogen to 6, we would need 2 of them. This would be an example where you could cross over and be okay to get you to the right formula. Again, doesn't work 100% of the time, but does work some of the time. Any question on type 2 compounds, how to name them, how to write the formulas? You need to be able to go both ways, from formula to name, and then also from name to formula. Any questions on any of that? Okay. Here's just a little decision tree as to, is it type 1 or type 2 and sort of which way you need to go. So I think the last thing we're going to talk about here tonight is polyatomic ions. And polyatomic ions are basically groups of nonmetals that have charges. And they have special names as well. So for example, if I look at NH4, NO3, and if I broke that up right about there, this actually contains 2 polyatomic ions, NH4 plus, and this 1 nitrogen and those 4 hydrogens all stay together as 1 unit, and the whole unit has just a +1 charge. And you do have to memorize the polyatomic ions, so there'll be a chart coming up, and maybe online I posted a chart. You are responsible to know the names of the polyatomic ions and the formulas, and obviously the charges as well, so you can write the formulas correct. Looking at the NO3, that is NO3 minus. So that is 1 nitrogen and those 3 oxygens. They stay together as 1 unit, and that whole unit has a -1 charge. So this nitrogen and the 4 hydrogens will never break apart individually into nitrogen and hydrogen or anything like that. They move around as units. Same thing with our nitrogen and oxygen here. The reason they don't break apart into individual ions or anything like that is, although the entire thing here for both of these guys are ions, they are actually made up of something that is covalently bonded together. So if you drew the Lewis structure for NH4 plus, it would look just like this. It is the sharing of electrons that's happening. And if you drew the Lewis structure for our NO3 minus, it will look something like this. So basically, this is why they don't break apart into individual things, because they're sharing electrons, they're covalently bonded together, and that's why both of these things will move around as units. And overall, though, these units, this guy has a -1 charge, this guy has a +1 charge, which is why when we put these together, we essentially just need 1 of each of them to get NH4 and NO3. These each have a special name. NH4 plus is what is known as the ammonium ion, not to be confused with NH3, which has no charge and is known as ammonia. Yes, different things. Yeah. And over here, the NO3 minus is the nitrate ion. And when we put two polyatomic ions together, we simply just use their names. So this would be known as ammonium nitrate. Any questions on that? I will say that probably right here, ammonium is probably the only positive polyatomic ion that you'll come across. Usually is the only one that you see. And what that means is, typically speaking, when we talk about polyatomic ions, is because almost a vast majority of all of them are negatively charged, they typically will end up with a metal, which means when we have a polyatomic ion and a metal that comes together, we essentially can name them just like we did with type 1 or type 2. And basically what that means is, just like in type 1 and type 2, it is the metal that's the most important thing. So if the metal is a type 1, no Roman numeral. If the metal is type 2, then yes, you do need a Roman numeral when you name it. So if we take, for example, Na, NO3, again, we could break it apart right there. This is sodium, which is group 1 with a +1 charge. This again is our nitrate with a -1 charge. So because this is group 1, it has that fixed charge. It's really a type 1. We would just call it sodium nitrate. As opposed to if we let's come back here and scribble on this page. As opposed to if we took something like Fe, NO3, 2. This would be iron, which is a type 2, which means it does need a Roman numeral. And we would still have to figure it out, but we would still know what this is once you learn the polyatomic ions. As we saw on the previous page there, that is NO3 minus. Again, there's not just one of those guys, but there actually is two of them, which gives us a -2 charge. That means in this case, iron is going to be +2. And if we were to name this guy here, this would be iron Roman numeral 2. And even though there's two of these nitrates, we would still just call it nitrate. And again, the 2 is the same thing as we did over here. Question on that there. This also brings us to a good point here. We do put parentheses around more than one polyatomic ion. So if you have more than one polyatomic ion, you need to put that polyatomic ion with parentheses and then the number on the bottom. And that is because if I did not parentheses or put parentheses around that, and I just wrote it like this, this is not good, because this basically means that I have 32 oxygens in this case and 1 nitrogen, which is essentially not what you're trying to say. You're trying to say that you have 2 of these NO3 units. So that's why whenever you have more than one polyatomic ion, you always got to put parentheses around it and the number on the bottom. So because these polyatomic ions essentially will always end up, usually, I won't say always, but 9 times out of 10 end up with a metal. You could treat it like a type 1 or type 2 compound, where if the metal needs a Roman numeral, you should include it. If it does not, you don't need to include it. And then in terms of the polyatomic ion, you just simply use the name of it, even if you have more than one. Any questions on that? So I kind of clicked through that list there. Let's go back to it here. This is a chart, and you have a similar chart, I think, in your book, and I might even post an earlier one up as well, of some common polyatomic ions. And as was a question earlier, you are responsible to know both the name, the formula, and the charge so that you can balance it out. There is a mistake here on this one. Cross it out. This is NH4 plus. So you get rid of that as well. So a good way to learn these is to group them together. So when you look at this chart or some other chart that maybe it's not so wow, is you could group them together by things that are related. So oftentimes there's groups of two. So if you look at NO3 minus, NO2 minus, NO3 minus is what is known as nitrate. NO2 minus is nitrite. And really both of these, this is one nitrogen and two oxygens with a -1 charge. This guy is one nitrogen and three oxygens with a -1 charge. If we look at something like SO4 2 minus, which is one sulfur and four oxygens, has a -2 charge, and SO3 2 minus, which is one sulfur and three oxygens, that has a -2 charge. This is what is known as sulfate, and this is sulfite. And what you can see here is really the only difference between these guys is the number of oxygens. And the same thing here. The only difference is the number of oxygens. And in a group of two, the one with the most oxygens will typically end in ATE, like we see here with nitrate and sulfate. Now, the one with the least number of oxygens will typically end in ITE, like we see here with nitrite and sulfite. So that's a really good way to memorize these. Sometimes people will remember all the eights and know that the ites are just one oxygen less, or vice versa. You could remember all the ites and know that the 8 would be one oxygen more. Because the charge won't change, the charge will remain the same for those guys in those groups. Sometimes people will just remember one of them and either add an oxygen or take away an oxygen. Now, there's also groups of 4, which are common as well. And the most common sort of group of 4 that are related to each other, we see over here in the table, is right here. And that is basically our ClO4 minus, our ClO3 minus, our ClO2 minus, and our ClO minus. And these are all basically -1, as you can see here. They all have -1 charge. The only difference is the number of oxygens in this sort of group of 4 that's related to each other. And if we kind of split it right about there, everybody on this side has the least number of oxygens in this kind of group of 4. And that means that they should end in ite. So this would be chlorite. This would also be chlorite. Obviously, you can't have the same name for two different things. So when you reach a group of 4 that are related to each other, the one with the least number of oxygens in that group of 4 will end in ite, but it will also start with hypo. So that is what is referred to as hypochlorite. This is chlorite. Now, if we look over here, these have the most oxygen. In a group of 4, which means they should end in 8, and they do. This would be chlorate. This would also be chlorate. But same deal, we can't have the two names that represent two different things, or the same name that represents two different things. So the one in a group of 4 that has the most oxygens will also start with per. So ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus That is perchlorate, chlorate, chlorite, and hypochlorite. And the reason why this table is so big is because if you switch out the Cl for another halogen, they were named the same way. So that would be perbromate instead of perchlorate. That would be bromate instead of chlorate. And same thing over here. So here, that takes care of most of this part of the table. If you put the iodine in there, it will also be named very much the exact same way. So you could pretty much swap out the halogen for any of those halogens, and you'll have a group of 4 that's related to each other. So when you have a group of 4, the most oxygen starts with per and ends with ate. The least oxygen starts with hypo and ends with ite. And the 2 guys in the middle are kind of named the exact same way as these guys, with ate or ite at the end of it. Question on sort of those groups of 4. Now, a couple other things that you also see as you go through this chart are a polyatomic ion chart. For example, if you look at something like CO3 2-, that's 1 carbon and 3 oxygens bound together. That is what is known as carbonate. And sometimes we will put an H plus in front of it. And when we do, that becomes HCO3-. And a couple of things change. We put the H in front. -2 + 1 gives us a -1 charge. We essentially put hydrogen in front of it. So the name of this becomes hydrogen carbonate. And of course, it's chemistry, so there's got to be another name. This is known as bicarbonate as well. And sometimes people will use bicarbonate instead of hydrogen. So if somebody says hydrogen carbonate or bicarbonate, is basically the same thing. You could also see that with sulfate. If you put a H plus in front of it, HSO4-, this becomes hydrogen sulfate, or again, just sometimes referred to as bisulfate. So for the most part, everything that's a polyatomic ion will end in ate or ite, but there are some that actually do end in IDE. So just gonna grab a green. So if we look over here, for example, this is what is known as azide, ends in IDE. Cyanide ends in IDE. A very popular one, right, is hydroxide, right, which is this one. Just writing it because I got 30 boxes on my screen. I can't see where it is on the chart, but hydroxide, which I think is actually right here. There it is at the top. Also ends in IDE, but for the most part, most of the time, the polyatomic ion will end in ATE or ITE. Any questions on sort of how to approach memorizing these guys? So again, just to finish up, just take a couple look at some of these some examples of naming these things and so forth. So if we had something like CaSO4, if we had something like Cu2, SO4, Fe3, oops, come here, 3, PO4, 2. And if we had ammonium sulfide, and let's just do nickel 4 cyanide, and calcium hydroxide. So if we go through these names, and we'll go through them here together since you've been hanging in there with me for all night here. So taking a look first at this one, again, we have a metal and our polyatomic ion. And again, the important part here is our metal. This is calcium, which is group number 2. So that means that calcium has a +2 charge. Again, here, when you learn those polyatomic ions, if you don't know them already, that will be sulfate with a -2 charge. So that is why we do have +2 and -2, just one of each of them. But the calcium is the important part. It is a type 1 guy, which means we don't need any type of Roman numeral. So this would be calcium sulfate. Any questions on that one there? Looking at the next one, again, we have Cu, which is copper. And that is a transition metal, which means we do need to figure out the charge. It should also tell us that it is type 2, which also means we need some Roman numerals with that guy as well. So in this case, we don't have just one copper, but we actually have 2 of them here. And we do just have one sulfate, which is a -2 charge. That means in this case, actually, each of these coppers to balance it will actually be +1, not +2, like some people might want to write. And this would then be copper Roman numeral 1. And again, we'll just use the whole name of our polyatomic ion, which would be sulfate. Again, the 1 for the charge that's on the metal. Question on that there. And looking at our last one, if there is none, our last one here is iron, which again is a transition metal, which means we do need to figure out the charge. We actually have 3 of those. And over here we have phosphate. Phosphate is PO4 3-. And again, we don't have one, but we do have 2 of them. So that is a -6. That means in this case, each of these irons up here, because there's 3 of them, will have to be +2 in this case. And I will come down here and write it. That means that the name would be iron Roman numeral 2. And even though we have more than one phosphate, we still just use phosphate as the name. And again, the 2 is for the charge on the metal. Any questions on naming those 3? Okay, now these 3 that we do have names for, we want to go backwards. So just like normal, if we want to go backwards, we just want to write the basic units that are there. So ammonium is, again, that polyatomic ion, which is NH4+. And sulfide is actually from the periodic table. That is sulfur, which is group 6, which is a -2. So when we take -2 and +1, we actually need 1 more ammonium there. And because that's a polyatomic ion that we have more than one of, we do need to put the parentheses with the 2 on the bottom to indicate we have 1 and 2 of these ammonium units. And here our S would just be 1S there to balance it out. Any questions on that one? So again, you want to make sure, because it is the polyatomic ion, that you do put the parentheses around it. I'll come down here to this guy. So calcium, which is group 2, has a +2 charge. Hydroxide, which is a polyatomic ion, is OH-. In this case, we're going to put +2 and -1 together. So we need not 1 hydroxide, but to balance it out, we do need 2 of them, which means Ca Again, you need the parentheses and the 2 on the bottom to indicate that you have 2 of those hydroxide units. Any questions on that one? And lastly here, we have nickel 4. And again, the nickel 4 tells us that we have nickel with a +4 charge. Again, that is what the Roman numeral stands for. The cyanide is Cn minus. So in this case, we actually need 4 of these guys over here to balance out the charge. So our formula would be NiCN. Again, you're going to need those parentheses and the 4 on the bottom. Any questions on polyatomic ions, how to name them, how to write the formulas? All right, so that is pretty much all naming except for type 3 and acids, but I think we've done enough obviously for tonight. So next week we'll tackle the rest of naming, and that should hopefully put us a little bit back on track. So again, hopefully by tomorrow or so, these will be uploaded if you need to look at them again. Other than that, I'm going to stop lecturing at this point, and a reminder that this is from chapter 3 is really in your book where you would find this stuff. If you have questions about anything else, feel free to ask. Otherwise, thank you for hanging in there with me. I appreciate it. And I'll see you guys virtually, I guess, next week. Yeah. Okay. Let me get your question again. If you have questions, I'll be happy to answer. Yeah, so it's okay. You know, I don't know. It might be easier for you to do a PDF or not. I think it should work out okay. I think it should accept a Word format for the experiment 7 lab report. So I think when you go up online, I think it will accept it in that format. So I think you pretty much could upload in kind of any format, most of the formats in terms of files, and it should take it okay. But sometimes if you make a PDF file, it just kind of uploads nicer and stuff like that. But I think it should be okay in the Word file as well. Again, if you have any other questions, feel free to ask. You're welcome. Thank you. You have a good night as well. All right. Have a good night, everybody, and a good weekend.